Hello, today we're going to be doing homework 3 in its entirety. In homework 3, there are 3 different parts designated as Part A, Part B, and Part C. For Part A, we are going to be deriving the differential equations governing the rate of change of liquid molar holdup and mole fraction of the more volatile component in a distillation column. Assume constant molar flow rates in each section, such as the rectifying/stripping, negligible vapor dynamics, and a vapor flow to the condenser that is perfectly controlled up to match the sum of the reflux and distillate flow. The liquid flow rates can be assumed to follow the L equals W holdup minus holdup naught to the 1.5 power, where holdup naught is the holdup at which zero liquid or no liquid overflows the weir on each stage. This ignores the bubble volume entrained in each liquid. Bubble volume entrained in the liquid. For part B, I'm going to read out this whole thing because I can. A column has two equilibrium tray stages between the total condenser and the feed stage, and two equilibrium tray stages between the feed and reboiler. The feed flows in at F equals 1 mole a second, with Z equaling 0.5 mole fraction of the more volatile component. The relative volatility is assumed constant at 2, and liquid flows via overflow at the rate of 12 times the holdup minus holdup naught to the power of 1.5, where holdup naught is 1.2 moles for all stages. The trays are filled throughout initially with the feed liquid at a holdup to yield liquid flows consistent with a distillate flow rate of 0.6 moles a second at a time, or 0.6 moles per second at a reflux ratio of 1. The condenser and reboiler are also filled with the feed liquid at initial holdup equal to 10 times the holdup in the rectifying and stripping sections respectively. A proportional level controller with Kc equals 1.5 is used to adjust the bottom flow with the reboiler holdup as a control objective, i.e. the bottom flow equals nominal B plus 1.5 times reboiler holdup minus 12 moles. Nominal B equals F minus D equals 1 minus 0.6. Stimulate the time response of the compositions and holdups in the column over 500 seconds. For part C, part 1, we are to stimulate the time response of the column in part B over another 25-second interval as the reflux ratio is stepped up from 1 to 5. And then for part 2, create a series of 4 McCabe-Thiele diagrams showing the time-varying response of the column as the reflux ratios are increased. So what I'm going to do is I'm going to get up on the board for part A and derive our differential equations, while also talking a little bit more about B and just making it a little bit visually easier for you. Because while I could just be doing A without drawing a column, I'm not going to do that because it'll be easier for you to visualize exactly what I'm talking about if I draw the column and work our way down. And from there, once I'm finished with A, I am going to switch over to B, which will be all in code form, and I'm going to write down a lot of the givens here, such as this equation where we have our Francis Weir as an example, or our alpha at 2. And there's also a few different things I'm going to have to explain as we go along. And then after that, we're going to get to part C, where I'm going to augment what I've done in part B. And then for part C2, we get to create McCabe-Thiele diagrams for this system. So I'm going to be right back and on the board.
All right, let's get started. I've messed around with the lights, and this is the best configuration I can find that actually has the board not being really glary. So if you really can't see, I'm sorry, but I will enunciate to make sure we can make up for that issue. So what we have here is a distillation column, very similar. This is exactly what ours looks like, just on drawn form, not in text form. So what this looks like is we have our feed coming into our distillation column, and as you said in B2, or in part B, we have two feeds in the rectifying section, which is the point of, which is basically anything in the column above our feed tray or our feed line. And then we have two trays right here in our in our stripping column, or our stripping section, which is anything below our feed line. And then, if we're just already on the bottom, we're going to look at our, what's down here is we have our reboiler. What a reboiler does is essentially when we have all of the things that aren't being vaporized up here, it goes down, goes through the tank, and then goes through our reboiler, which really heats it up, it cooks it, it vaporizes our material again before it sends it back through the distillation column, or it sends it on its merry way. And we have the same thing at the top, where we have our vapor that goes through all the way at the top, through our condenser, which condenses our vapor into a liquid before it splits. It either goes to L, which is our liquid coming back to our column, or it's D, which is our distillate, or your product. And this is what a tray essentially looks like. Actually, I'm getting ahead of myself. And how we number these trays is important. So the way we're going to number it is our condenser and our reboiler actually act as their own tray or their own stage in this column. So it's going to go from 0 then to 1, 2, and we're going to actually call our feed tray a tray, excuse me, oh man, 2, 3, then we have our two trays on the stripping section, 4, 5, and now down here we have 6. Number 6 is going to be our reboiler. So we actually have 7 sections because we go from 0 to 6, and that's just the way you usually are going to enumerate these things. And then to go back over here, what we have is an example of what a tray looks like. So what a tray looks like is we have our heat or our molar amount of moles on the tray, and what happens is we push vapor through and then liquid falls down. So we get this interface where we hope that we actually get to equilibrium. And what we end up getting is we have V, so our vapor from below. So if we're going to use number 2, for example, we have Vn plus 1. So our vapor that's just came through tray 3 goes up to number 2, and then what leaves tray 2 is Vn, so the vapor from tray 2, essentially. And then in our liquid portion, we have what's coming down is liquid Ln minus 1, which if we're looking at 2, is liquid that just fell from this tray number 1. And then what we have over here is Ln, or the liquid that is then leaving our tray. So that would be L2. So what we have is we're going to first do a change in moles. So we're going to do dx over dt, or dm, sorry, because dx is the change in composition, dm is the change in moles. So we have dm dt, and we have what's coming and leaving. So we'll have Vn plus 1 plus Ln minus 1, I believe, plus this red is kind of rough. So then we do plus Ln minus 1 minus, we're going to have what's leaving, so Vn and Ln minus Vn. So next what we're going to have is our change in dm over dt. So what I'm going to do is I am going to actually erase the board. I might put this equation up here, somewhere smaller, so then I have more room to write, because right now the board's a little cramped. As you can see, I'm kind of running out of room. So I'll be right back. All right, so I rewrote our equation on the board. It's really small, kind of hard to see, and then I also erased our representation of a tray and just moved this really small version up here because it's really helps me to remind me of what I'm actually doing here. So now what we're going to do, now that we have our dm, we're going to do dm dt times x, so the change in concentration, over dt times x1, which end up getting Vn plus 1 because it's a vapor, or do times yn plus 1, so the composition. And we're going to do the same thing, plus Ln minus 1 because it's a liquid, we're going to do times xn minus 1. And now it's the exact same thing with Vn and Ln, so minus Vn times yn minus Ln times xn. And what you end up getting over here is a product rule. So you end up having dm over dt times x plus dx over dt, I believe, which equals this same lovely spiel. So we're just going to not write that down, so it equals that. And what you end up getting is you can plug this part down here. So you can end up get, excuse me. So you end up getting, if we just put x over on the outside, Vn plus 1 plus Ln minus 1 minus Ln minus Vn dt. No, sorry, that is dm dt, excuse me. Plus I believe dx dt. Now I'm going to flip over here. Equals, we have our Vn plus 1 times y, times yn plus 1 plus ln minus 1 times xn minus 1 minus vnyn minus ln xn. And this is the governing equation, I believe. And what this really ends up showing us is that we have the compositions really affect what goes on, because just they're in every aspect of this equation, or of this problem. So what we're going to do next is we are going to, and this is x1 and x1. It's important we have to denote that. So what we're going to do now is I am going to get to coding, and we are going to really start plugging everything in. But while I'm coding, I'm actually going to transfer all of the givens in that problem onto the code beforehand, just because there's a lot, and I don't want to keep flipping back and forth between pages as we start to go about this problem. So I will be right back. Seems that I lost a term. Sorry, I'm actually not coding. I was just about to erase the board before I realized a mistake, and I needed to make sure I corrected that. So while I did the product rule, I actually lost a term. I lost multiplying it by our m value. So what this would be here would be dm times dx over dt. Well, everything else remains the same. I just lost my m term doing the product rule. And now we can get and cut back to the code.
All right, now that we have derived it on the board, which is directly in front of me, we can now start to actually solve this problem. So the first thing we want to do is actually calculate our bottoms. We're still trying to set up our bounds of this equation. So our bottoms are going to be basically what's coming in minus what's going out. And because we know our feed is coming in, and the only thing that's leaving we know is our distillate, so and the only thing else besides that would be our bottoms, because it would be f minus d minus b equals 0, theoretically. So now we also want to calculate the L top, or the liquid that is coming out of the top, which is essentially our reflux ratio, but the way that's like described. We want to calculate our L top. The way we're actually breaking everything up is basically tops and bottoms. So we have L top, we're going to have L bottom, I believe. Then, I don't like this. L bottom, oh my gosh. L bottom. Then we're also going to have our moles on the top, and our moles on the bottom. And this is important because the reason these would be different, so for example, our liquid on the top, that is essentially just going to be our liquid that's coming back from our reboiler. And we can calculate this using the Francis-Weir equation. That's the wrong thing here. So Francis-Weir is L over W, which is the constant. So we're going to do, let's see, over FW, constant, what was it? Let's see. And that's, so we're going to do L over W. Oh, I'm missing that. Plus M naught. And actually, this is not how we solve for LC. This is how we solve for MT, the amount of moles that are flowing. And so for the top, it's going to be LT, or why is it like that? LT plus M naught. And it's going to be the exact same thing for the bottom, except that it's going to be our liquid at the bottom. So our liquid at the bottom is essentially going to be our liquid that's returning, or let's see. So we have F, T, because there's an equation that we can solve for, that we can do L times, or where is it? I want to say it's R times D equals L. So L equals, L top, there it is, L top equals R times D. Because R, if we look up reflux ratio formula, R equals L over D. So if we want L, we have R times D. And also one thing I missed, we also need to calculate our vapor top. I hate this. Our vapor top, our vapor bottom, and again, the reason is because we have our feed coming in as, let's see, where is it? Homework 3. It says Q is, okay, it doesn't say it in here, but when we're doing the problem, it says that Q is 0.9. And what Q is the fraction of our feed that's a liquid. So, I'm saying, actually, we can just look it up. What does Q mean for a distillation feed? I can't spell. It's the mole fraction of the liquid. So if we know that Q is 0.9, we know that the liquid of our bottoms are going to be our L top plus our Q times F. So the amount that's going to be trickling down plus the feed, exactly. And that's going to be kind of the same thing with our V top is going to be, actually this is going to be the opposite, because our vapor of our bottom, this thing. So the vapor that is at the top of our column is going to be our, I want to say it's just going to be our distillate, because every distillate plus LT, because everything that goes up to the top of our condenser condenses back into a liquid. So I might be going about this wrong. So that's everything from the top, and I feel like I'm going about this wrong because I feel like we need to include Q. And the vapor in the bottom is going to be VT plus, I'm going to do 1 minus Q times F, because it's going to be essentially what is not a vapor in our feed. So if we do that, the next step is we want to create our initial conditions. So we're going to have Xi, and which this is basically our original mole component of everything, in which I believe that was given. I think it was given, because our Xi is just going to be like, we need to create an array, because this is basically our going on each stage. So NP, I did not hit this. NP.array, and we're going to do, what we want to do is like a shape, so we're like Xi is going to be, let's see, what was it? What would be, this is our component, not the amount of moles, our component of everything. So it'd be Z comma N, I think. Let's see if that breaks. Alright, So what I want to do is, and I think I just want to do like NP shape. All right. So the goal of this is to actually create our array and then our shape. And then we also need one more initial condition. But I want to make sure that what we have, make sure this is out of the camera's way, I want to make sure what we have is right first, so I'm going to cut and we'll be right back. Alright, so I found a few, this is not really a mistake, I just really wasn't thinking. It's NP full is really what we wanted. Like that. Fill. I mixed up full and fill. NumPy has no attribute. Fill. Well, I know that's right, so we're going to skip it, to be really honest. Also, I forgot to put these up to the power of 2/3, which might cause an issue if we don't do that, so we're going to do that now. So the next part we want to do is our mi, basically our moles, our initial moles. That's going to be np.r underscore. We're basically creating our row or our array of values, starting at 0 and then going all the way to the end. So first, we're going to start all the way at number 0, which if you remember from our derivation earlier in the video, 0 is what we call our condenser. So that's going to be 10 times our moles at the top, and then we have we have tray 1 and tray 2. If you see me looking up, I'm actually just, here, I can pull this one. I'm actually just looking at the board where I still have everything derived. That way it just kind of helps me with like what I'm trying to remember wise on like the numbering system. So, then we have MT, and we're going to do MT. So he did it in the video, we can do, I think it's MT, we do 2 times, which basically just does it twice. And then we're going to have 3 MBs, because we can count our bottom 2 in the rectifying section, our bottom 2 in our stripping section, which also accounts for our feed. Because the only thing the difference between MT and MB is one is above the feed line and one is either equal or below, which is important because it changes the composition. Then we have 10 times MB. I swear, I never get this right. You know what? I don't care. Clear. Now we're going to define our right-hand side, where we have, we're actually having 3 things defined. I think it's like a lambda, t, and then a vector. I may have the order wrong, but the first thing we're going to do is x comma m, I believe is how we're going to name these. And it's going to be a split vector. Essentially what we're doing here is we're separating our this vector that we have, right? Because after this, we're going to start solving for everything individually. Like, for example, I know we're going to be solving for L naught, and we're going to start creating everything in arrays, because as this system changes, some of its values are going to change, which is why it is actually going to be in an array. So, let's see, what's the next step? I hate how this isn't indented. Alright, L naught. I think I'm getting a little ahead of myself with this. So, we're going to have X, M. Actually, I'm going to double check. Also, I'm just going to check the actual syntax for this, because it's just going to annoy me when I can't actually complete this box. So I'll be right back. So I found my issue, because of course, it's always something so simple, where full creates the array for you. So or not. Unsafe? What the heck? Z comma N. Well, okay, now I'm just annoyed, but who cares? So this is going to be T vector, independent, dependent, and then R. Because R is going to be changing. And NP split, we do vector, can count 2, I believe. Right? Alright, and now we're going to have DMX, DM. Why is it always, I don't understand why it always goes exactly to like this stupid thing. And then we do V L, and it's going to equal make, not make, we're going to say, yeah. I want to fill this with zeros, like make array 0, comma M, or comma X, and then everything else is the exact same thing, but in terms of like M, because they all determine on M. Our vapor determines on M, and this determines on M, but ours doesn't. Oh, I don't do that. And then what we want to do is we're going to recalculate our L values, or our vapor values. So we're going to do V equals, let's say V T VB equals, because we don't want to just put it in D, we need to put it in terms of R. So it's going to be, I think we have to calculate LT again too, if we're going to, yeah, LT equals R times D, VT, right? It's R times D, so it's going to be R times R. I'm confusing the heck out of myself. So VT equals D plus LT. D plus LT, which is R times D. Alright, perfect. And VB, that should be the same, because everything is already like calculated, like recalculating inside of here. Let's see. I don't know if we actually have to recalculate LT, to be completely honest. So our liquid, and then we need to, actually we're gonna figure this out. Numpy make array full of zeros with a specific shape. Okay, np.zeros. Alright, we're going to do np.zeros like x. We're going to do np.zeros like m. I'm copying and pasting it because I feel lazy. And it didn't break so far. So what we're doing, let's just rerun over this homework. We are basically calculating the change. And what we're doing here is we're setting up our arrays, and now we are going to be calculating the change in our x's and our m's, our distillate, our amount of moles, and the composition of our moles. We're counting moles as kind of like our material in the system. So then we can start calculating. We are going to calculate L naught, and while we're at it, actually, actually I won't do that yet, because what I was going to do was they give us this value and over here, but I won't do that just yet. Just need to calculate a few more things. So calculate our liquid at 0. Let's see, our L value. I'm trying to think. L at 0 is basically just LT, so it would be VT, I would think. I'm getting a little turned around here now. I'm gonna make sure I'm following the right path, because I think what we do is we calculate our L values, our liquids and our vapors, and then, oh, actually, I know what I forgot to do. We need to calculate our equilibrium curve, which is important. So this is equilibrium curve is y, and we're actually covering this in our separations class. So it's going to be alpha x. It's going to be alpha times x divided by, let's see, it's going to be 1 minus x minus alpha times x. That works. Yeah. So now what we're going to do, I'm going to be right back and double check we're going the right path, and then we will continue to solve for the right hand side. So I was being a little dumb when I was doing this. This actually is L0 equals R times D. Get rid of that. Now we need to create our arrays for our vapor and our liquid. Vapor equals that, and we do liquid of, let's see, it's going to be 1 to, oh, that's not what I wanted, 1 to negative 1, so if we're starting at 1 all the way to the end, is going to equal this funky little equation we got here. So L equals W, let's see, Francis, what do we call this? F weird? FW. FW constant times M to, I believe this is going to be, yeah, it would be M, and be to the 1 to the negative 1 minus M naught to the 3 over 2, right? Yeah, M minus M naught to the 3 over 2. And this is our vapor is going to be another new array, in which if we want to think, we start right after the condenser. It's going to be 0. This is the amount of vapor. Then we're going to do VT times 3, right? Or times 2, because we have our 2, comma, then we have our, is it 2 or 3? Because, let's see, honestly, I would think it'd be 3, because we still have vapor coming in, like we still have our vapor that's coming like from the top, right? The top vapor. It's coming in at the feed line. So I would say it's 3 times VB times 2, right? Because that gives us 0, it's at N0, N1 through 3. So we have 0, 0, 1, 2, 3, 4, 5. And then it would be VB times 3, because the bottoms. We have, including the reboiler. Maybe. And then, one thing I realized up here is I had my order switched, which is actually kind of sad. Z. So finally that nasty little error is out of the way. Let's see. That works so far. So now, we can do KC equals 1.5, and we're going to do, we're going to call the next part controlled underscore B, because that's essentially what we're doing here. Let's see. And it is bottoms flow. So wouldn't that be, what are we calling this? So vapor, liquid. I'm just going to keep it as B for now, and we'll change it. Plus 1.5 times reboiler holdup minus 12 moles. Okay, our reboiler holdup is 10 times MB, I think. Because what we're doing is essentially, we have a valve, right? And this valve is essentially saying, hey, 10 MB minus 12. If MB, or our moles of our bottoms, like that are occasionally coalescing in the bottom, is more than 12, open the valve and start. Basically, this is just controlling, right? This is all it is controlling. We want to do an if statement. If control B is less than 0, then then control B equals 0. That's essentially what I want to say is like if control B equals 0, then I think that makes sense, right? Because we don't want this to be a negative value. Like, for example, if MB is like 0.5, this is 1.2, let's say it's like it's 1. So we have 10 minus 12, negative value, plus whatever we have set. We just want that donezo. But now we can keep, now what we're actually going to end up doing here is our full like big derivation that we did earlier. So we're going to have dm equals that, and dmx equals, because those are what we solved or what we derived earlier. But I am going to, before we get any further, make sure there's no errors with my arrays that are going to be calling these values into question. And I'm going to make sure this is actually right, because I think this is right, but I also think I could do this in a better manner. So I'm going to be right back. So something I didn't realize was I didn't actually set this up as np dot r underscore, which actually helps. Also, I need to double check. Oh, this was it. So one thing, I could have just put KC, that's why we named it. And what we want to do is L dash negative 1. So basically the end, or what is in the reboiler, equals control B if control B is greater than 0, because if it's not greater than 0, that means we have less flow. And then else equals 0. Invalid syntax. I don't care. I know what it means. So the next, now we want to do is calculate dm and dmx for different times. So for example, dm at, what is it, like negative, I think we can set negative 1, like negative 1 to 1. Because I don't think we want to do that, because we have dm of, wait, which one is the feed? It goes 0, 1, 0, 1, we have 3. 3 is the feed. Because you know 3, all it is just equals f. Because for dm, it's just the actual flow of, it's just moles. We don't care about composition. So that's what I wrote up here when I was like what we derived earlier. So everything except for this is why we're going to do it earlier. This is from between to between. Equals, we're going to do v to n plus 1. Oh, it's a t, geez. I just need to fix that because that's going to annoy me. 1. So V n plus 1, so that'd be negative 1, n plus 1 would be below, and negative 1 to 2, and we're just going to keep it as that, and then plus L n of n minus 1, so 1 above. We're going to do, so actually we're going to do this negative 1 to 2, and then we're going to do L, so then crap, I'm getting confused now, son of a gun. Because I know we're going to have to set up dm equal dm, I think we have to set up dm as 0, and we're going to have to set up dm of negative 1, which then makes no sense why we're doing this here. But anyways, we're going to do minus v, and when we minus v, it's going to be exactly what is on here, because I'm fairly certain negative 1 to 1 minus L negative 1 to 1. And dmx is essentially the same thing, but remember we have to multiply by the components. So it'll be the x value, the y value at each specific interval. But I'm confusing myself with the n values, or essentially what iteration or what are we on the tray 1, tray 2, tray 3, and how it's really affecting each step. So I'm going to be right back and I double check that. So what I found was we just don't even need this equal sign here, and that should work. Also, this should be 2 dash, and this would be L would be 1 to negative 1, because vapor and our liquid have very different ending points. This would then be, I want to say negative 2 dash, or it might just be dash negative 2, actually. And then this is, again, I mixed up the order here. Negative 1, and don't forget to do plus equal F, because it's essentially the same thing as the feed plus whatever liquid is falling down from above, meaning we're going to have to basically add it to itself. And then dm0, or what's in the condenser, is essentially V total, so we're going to do, what is it? I think it's V dash 1, because is everything from the vapor from the first tray is all going to go to the condenser, right? Minus D minus R times D. And then the vapor that is in our, change the moles of our, our reboiler. I don't remember. But anyways, we can just switch to dmx, and then we can go back to it after. So dmx of, let's see, where's this, 3, dmx of, what is this, negative 1 to 1. Actually, this might be 1 to negative 1 too. Son of a gun. And we're going to do dmx of 0 and dmx of negative 1. And all we're doing is multiplying these values here by their components. So this would be, let's see, V1, so we're going to multiply V1, because it's a vapor, times Y to the exact same tune. L, which is then times X of, where is it? 1 to negative 1. Minus V, 2 dash, times Y, negative 2 dash, which just might be wrong. And then times minus L times X to the 1 to the negative 1. Vapor 3, can't forget this funky looking thing, which is F times, I feel like Q would make sense, or not, no, because of composition, so we're going to do that, we're just going to do, shoot, because it's a combination of both, specifically on that one. Well, we're going to skip it. So, we're going to do B1 times Y1 so the change in concentration, and because D and RD, aren't they all, oh, where are they? They're all liquids. Yeah, so it'd be X, I want to say 1 or 0, honestly. That's also a choice. Times, we're going to do parentheses, R times D plus D. And then I'm getting mixed up on the condenser, because if we want the change in moles of the condenser, we would have our bottoms, right? Everything, so we would have like, the liquid 0 on, right? Or not 0, and minus 1, so it'd be minus 1, that'd be like, I don't remember. But the one right before, so wouldn't that be 6? Ooh, I don't know. Okay, I don't want to do all this guesswork. I'm going to double check what I have is right, and I'll be right back. So I was right. I just didn't want to put it, I shouldn't have put it like 6 dash. Just put, we want only the negative 2, so the value before the last one. So minus negative 2 minus L, to the negative 1 minus V to the negative 1, the vapor that is leaving from this. This is just, again, a general mole balance for each tray. And let's see what else. And then I realized this is on the wrong side of the equation, so I go down here, change that sucker real quick in both places. And then, you gotta remember this would be Z, because Z, as stated here, mole fraction, the more volatile component, which is exactly what we want. Z, and then this should be a subtraction sign, and now we can do, let's see, L, so copy and paste this because I'm lazy. L to the negative 2 times L is X, and we do X to the negative 2 L to the negative 1 times X to the negative 1 minus, give some space here, and then V times Y to the negative 1. So now that that's all squared away, we can finally solve for dx, right? Is that what we're solving for? Yeah, because that's where we did the differential equation. I just didn't write everything out when I messed up my m previously. So dx equals, let's see, going to be, I'm looking at the differential equation on the board. Dx equals x1, x1 times dm divided by m? No, because you would just subtract the whole thing across. Anyway, and he would like return np.r. Shoot, what are you returning? You're returning the two things, right? we're going to return dx, and God knows who else, maybe dmx, because dmx relies on dm, so we'll know if that's off. Maybe it didn't work. Oh, it worked. So we're going to set tend equals 500. We can do res equals solve.ivp. Functions, we're just going to call this lambda because we can. Tspan, and we do tend. Let's see. Function. I don't get lambda. We can just do right hand side. T comma vector. Oh geez. Vec comma r tend. Because vector is right hand side, of course. Well, what's defined in there? It's fine. And then what's next? And why not? I think we have m naught and xi naught. Okay, so we want to return xi and mi. We return like dm and dmx, I think. dm and dmx. Okay, I'm going to be right back and double check I'm returning the right values because I'm a little concerned. I think we're solving for dx, but we're not bringing it back. I'm getting a little turned around with all the dx's, dmx, and I'm getting a little confused, so I'll be right back. So I found a mistake, a few of them actually, in which first it should be oh man, I'm struggling today. Like this is bad. We want this parentheses, dmx minus x times dm. That we want to return not dm, not dmx. But we want to return dm and x, I believe. Then solve IVP. This one's going to get lengthy. It's going to be lambda t comma vector equals RHS t comma vec comma 1 and 0 comma t end. And then we're going to do the next step. It's going to be np.r. No, not the funky looking brackets. What do we have? xi, mi. We're going to switch this around. Maybe. I will leave this here. X, mi, comma xi, right? Sure. What do you mean that's an error? np.r underscore worked up there, but not over here, because of course not. That would be too easy. Function entity vector equals RHS equals, is it like that? Yeah, that. And then we want to do method equals redow. I spelled it right, probably not. I'm going to do tense underscore output equals true, and we're going to see if this, there's an error in my DM1. Could not broadcast input array shape from 5 something into a shape of 0 something. That's concerning. okay, but we know we gotta do like t plot equals np dot linspace start stop number 0 comma t end. Did it say how many iterations, like how frequently I wanted it? So it just says 500 seconds, so we don't really have a end. We'll just do 100 maybe. And we're going to do res.sol equals something. Make subplots. Make underscore subplots equals. Actually, I'm going to do figure equals make subplots. That you want one row, rows equal 1, columns equal 2. So we're going to make 2 plots because we want, again, we need to track our x values and our y values, which means, we're going to track our moles and our concentration, which means we're also going to have to unpack it. So we're going to do like x mi comma xi equals np dot split Alright, I'm getting turned around. This error is throwing me off. I want to double check like what's causing this, and then I'll be right back and we can finish part B. So I found a lot of issues. First is this should be dx dm, but on the bigger case, this is the big issue. It should be v, we're going to have minus, we're going to do plus L, right? And then because this is n, this is n, and this is going to be plus, this is plus 1, and this is minus 1. And then we got to fix all this kerfuffle over here, right? So now we're going to do minus v, and because it's a v, this is a y, and we got to do plus, no, this is an, don't do that. This is an L, right? No, because that's an L, this is an X, times L times X. Okay, that looks right. So shift, enter, that works, perfect. So we gotta do res 1 equals res dot sol, and then t plot, and for t plot instead of 100 we're gonna set this to 500 because we can. And now we have this in terms of xi and then m, so we have to switch this. So it's going to be an xi and then a mi, and no, if I hit enter. Oh, this is really concerning. I don't understand what is wrong with this. Like, it means there's something wrong with my v value. Oh wait, there might be something wrong with my v value. Because like this is either, so it says cannot broadcast input array from shape 5 dash into shape 0 blah. That does not sound good. So now we're going to xi comma mi np split array this is vector, or maybe right hand side. I don't remember right now. I think we want an axis of 0. And yeah. Okay, now that I think I know what might be causing this issue, I want to say it's got to be something with either our V values or our L. I am going to double check everything. I think it actually could be, maybe this isn't right and it's causing, but I need to actually go through, debug it, and when I find the issue, I'm going to Control Z all of the changes I've made, and we will then be right back. Well, I found my issue. First, and foremost, this should be from 1 to a -1, not from -1 to 1. Secondly, we're saying there is no r value. That's because of this bad boy was not correct. And then errors is vector is not defined. Our vector is technically this bad boy. So we're going to do res1, right? Then 2, because that's what we want to split into. How many splits, and then the axis, which is that. Boom shakalaka. And so there's that, and we want to do an enumeration. So for I would enumerate zip something. All this is doing is basically counting all the iterations and doing that, but I'm not exactly completely sure on the on the syntax for this, but I do know what we actually want to do is we do fig dot add underscore subplot. So add or create make subplots. Oh, it's add scatter, Jesus. Add underscore scatter. X equals tplot, y equals xi. I don't care, the mode's going to be in lines. I'm going to do that. Row 1, column 2. Well, it's pretty handy, I'll be honest. Name equals, we want to do this funky thing, right? Where it's f outside, iterable I, what do you want to call it? M. This is x value. Equals cf x, we're going to call it m, and then we're going to do this just so it's there. We're going to do figure, which isn't going to work because this is not invalid syntax, right? So I'm going to double check the syntax for enumerating and the zip value. I might even pull up the website to make sure. I'll be right back. I think I figured it out. Well, a few different pieces. This is going to be XS, this is going to be NS, because it is. And then we're going to do for I, comma, we're going to do X, comma, Y, in enumerate, zip, XS, comma, MS. And then this would just be Y, or X, this would just be Y. Okay, that makes sense. That's not right. Alright, let's try y equals x, y equals m. Right, maybe, that's probably what it was. Nope, m is not defined. Yeah, so there's definitely more issues that I have to find. MS, no. I think it should just be y. But, nope. Alright, I'm still going to continue to try and debug this and figure it out because I'm still just floundering. After debugging my code, I found a few inconsistencies. first and foremost, an issue I was having was that I needed to have, because I was putting it in 2/3 for for MT and MB, this needed to be in parentheses because 2/3 wasn't carrying over and caused some issues. Also, I found that when I was calculating VB, I should have put a minus sign here, while the whole time I had it a positive sign, like a plus sign, both here and down here, which was causing, again, some issues and why my graph was skyrocketing like crazy. Other things I found that could have, that made it wrong, was that in control B equation, you know, the one that was given, I should have just had to copy, I got it really wrong. This should have been m to the -1, basically the last value in the reboiler, minus 10 times m naught. And I didn't have that whatsoever, which again was causing issues. But eventually, when you run your code, you should end up getting something that looks like this. This graph really shows how your time, or how your concentration and your moles change over time. But yeah, now we can move on to part C. Alright, now we can start part C1. Simulate the time response of the column in part B over another 25-second interval as the reflux ratio is stepped up from 1 to 5. So, let's get this over with. We're going to copy and paste exactly what we have. We're going to change this to 25. We're going to change this to 5. We're going to change this to res 1, comma, -1. We're going to change this to res 2. And we're going to change this to res 2. And that should give us the desired answer. And boom, you can see the difference. And as we step it up over the time, it's not just a sharp drop-off, and then it slowly figures itself out. You can see here, it figures out, okay, this is where we actually want to be now. Instead of, you know, making it a little bit quicker, there's the change, as you can see, causes the fluctuation, which is great. So now, we can create a series of 4 McCabe-Thiele diagrams showing the time-varying response of the column as the reflux ratio is increased. So what this essentially means is we are going to, somehow, we want to split the time into 4 intervals, let's say 15 seconds, or maybe 16, what did it say? And we want to create 4 McCabe-Thiele diagrams. So let me make sure I'm up to date on my syntax, and we'll be right back and starting to do that. So now we got to do xs, ms equals np dot split. We're going to do res 2. We're going to do but 16. I believe that's all we need to do. And then we got to do axis equals 0. I think it's 2, comma, axis equals 0. Sorry, I keep getting a lot of text messages. And then we should be good for the next part, which just doesn't look like it's happy, but we're fine. Xplot equals np.linspace 0, we're going to do 0, 1, and then 100. And now we're going to do we're going to do figure 12 for some reason. Equals make subplots. This is helpful because I spelled rows 1, columns 4. And now we are going to, what is it AI doing? I'm just going to add this in because we can. But we want to do xs.t and ms.t because we can. And then, one thing we want to bring back down is our calculation for the equilibrium curve. Why is this angry at us? Oh, that's why. Because this one was bad. And let's see. Alright. I'm going to fix this, and we'll be right back, and we will continue working on this, and then we should almost be good to go. Now, we're going to be doing YMC and XMC equals np dot repeat, let's see, is it y1, comma 2? Oh, that's not. y1, comma 2, because again, we're doing the Cape deal, which is, here, we can just look it up. The Cape teal, I call it teal. Which looks something like this. We actually have to double our x and y values, and then use them at different points. And we have xmc equals, let's see, this is going to be I think it's like np dot r underscore. Are we allowed to do it? Wait. When we've done it earlier, am I allowed to use, okay, we're allowed to use brackets on this one. We're going to do x0, comma, np dot repeat, I don't understand why, what is this? And repeat, we're going to do x -1 to 1, comma 2 times, and then x -1, our last value. And then another thing we might want to do, and I figured out the issue up here, it's just because these are semicolons, or like things. We're also going to want to name this. Well, we don't have to, but naming them to like follow this is a whole kerfuffle, so we're going to keep that out of it for now. We don't want to do that. Now we're going to want to add scatter, x equals x plot, this y equals x, I plus 1. We're going to copy and paste, and except x is going to be m. Right, and we're going to see if this breaks. Too many indices for array. Array is one-dimensional, but 2. Right, I'm going to double check this, and I'll be right back. Alright, I found this issue. So first should be, crap, what do we just have? Should be 1 to the -1, and it was having this error because I had a comma instead of an actual thing in the doohickey, which causes this fugly looking thing, which is not right. And another thing that I realized we have to do is we need to actually create a y plot value. So it's a y plot essentially equals this, but every x is an x plot value. Let's get rid of that. Control V. So x times x plot minus x plot plus alpha times x plot. So now we have a y equals x plot, and then x equals x plot, and y equals y plot. Then we have a x equals xmc, y equals ymc, and then we need one more. The naming, I don't care about the naming. We're going to have to do mode equals lines, I believe, just because it causes some funky things if you don't. And I'm not going to be changing the color, even though we can. You can do like color or RGB, and you gotta do fig 12 dot add underscore scatter. I'm gonna do that. And it's like x equals like x naught, I want to say we do, and then y equals like y naught. Just setting up our points. I Let's see how broken this looks. Oh. Do y equals. That's not what you want to see. And it says, did I mean mode? Yeah, I did. C, invalid of type. The X property is an array that may be specified as a tuple, list arrays. Alright, so something was wrong within naming the array. So I'm going to double check this and I'll be right back. So I think I found a little bit of what might have been causing an issue, because X is already a, oh, I didn't want to do that. So X is already a value, and we want to specifically put it on points. So y equals 0, y equals 0, comma 1, 0, comma 1. Let's see. We do that. Clear output. Clear system output. Mode. I must hit Control Z too many times. Mode equals lines. Mode equals lines. All right. So what we're getting here is the first point, but not the others. And I think I know why. Oh no, never mind. I didn't think this was indented all the way, but it looks like it is. I wrote that, and then I do fig 12. No, yeah, I'm still only getting the first indentation. What if we move the order of this around? Like, put this in the middle instead. Just because, and I honestly just want this all in the same go. Fig 12, let's see, there's a break. Alright, and we're still only getting the first part of this, so let me again look into what's causing this, and I will be right back. So while going through my code, I was trying to think what would cause only the first value to show up and not the rest of them. And while I believe, well, making sense, it's only the first y value, right? The x value changes, but the y value doesn't. Meaning, if you look at our YMC, I'm just repeating the first value. If I put a colon here, or a semicolon, but I don't know which one is which, that way you goes from y1 to the end of time, or our iterations, you end up getting a nice, dandy looking chart, which is very different from our chart below. As you can see, this is our first, second, third, and fourth. This separates it in times of 16. So we end up getting our 4 different McCabe-Thiele diagrams, Thiele, whatever, which shows the time-varying response to the column as the reflux ratio increases. Because this is at time 16, this is at time 32, 48, 64. And please take my word for that. But that means we have successfully completed homework 3. Don't look at the time. I might want to go to bed. But thank you for watching, and yay.